The industry has really been built on point tools or task-oriented tools. And that's been fine for when you're at 90 or 130 or 180 nanometer. I mean, it worked well. So what's different with our approach relative to, say, what the rest of the industry is doing is we introduced something called silicon realization. And silicon realization is really this end-to-end concept of bringing design tools together, methodologies together in an end-to-end sort of holistic approach. Now we focus on three areas in particular. One is intent. Think of that as a design intent. What does the designer want to do, and how does that manifest itself throughout the tools? Abstraction, which is, there's a lot of data you have to contend with, gigabits or gigabytes of data that you have to manage throughout the flow. So you can't possibly optimize everything at the same time. So you have to find unique and very accurate ways to abstract the data up so that you can optimize where you need to optimize. And so abstraction is a very critical, and even more so becoming a critical element to the successful tape out of an SoC. And the third is convergence. And convergence you think is a natural thing, but convergence is huge. We think of convergence in the traditional sense as 3C, the computing, the consumer, and the content coming together. Well, that's true, and certainly that doesn't, as an enabler to the electronics design market, well, we have to also converge. And so while you think it's, maybe fairly straightforward, and to think about it, it shouldn't be that big of a challenge, just fold these independent point tools or task-oriented tools together, and voila, you have convergence. But it's not that simple because you have very different databases, you have very different design requirements in different spots along the flow. So convergence is really a challenge to do. What's making us different and why we're starting to get some critical acclaim is over the last 3 years, we put a heavy emphasis on how do we tie these independent point tools that we have a good presence in today in the market, how do we tie them together to provide a synergy that allows designers to get a faster design, more risk-free design out the door. And so what makes us different is the fact that we are bringing that intent, abstraction, and convergence to play pervasively through the design flow, whether it's a digital flow, an analog flow, or mixed signal or low power, you name it.
Okay, so give me some examples of intent. What are the kinds of things that we want to pass between tools as far as intent is concerned?
There's three fundamental areas. Functional requirements that you have for your chip. What is this thing going to do? You have electrical requirements. What are the specs it needs to hit from a performance standpoint or a power standpoint? Then you have physical requirements. What size does this thing need to be? What does the yield need to be? Those kind of elements. So when you start looking at all three of those things in connection, traditionally they're handled independently. You find out what does the functional thing need to be. It goes from a napkin to somebody's talking to you to maybe writing an email and sort of crafting some sort of spreadsheet that ultimately makes its way to a physical designer who attempts to lay it out, or a designer to lay it out, and then at some point throws it over the wall to electrical guys who says, you didn't meet the low power requirements that we have or the timing, so it starts again. So when you start pulling these pieces together, intent becomes really critical. So think of it as a functional intent. What do I want to create? What is the area at a system level or an SoC level? What does that area need to look like? Where do my IOs need to line up? What are the physical constraints that I need to have in place? How do I pass those throughout the entire flow? Well, I need an intent file. One of the clear examples that we pioneered was low power as a low power intent, or the common power format, or CPF file, which has become almost an industry standard. Many designs under the bridge for that. But that would be an example of intent. Another one would be constraints, pin constraints on a certain side in an analog world. Well, you have to at some point pass that design over the wall to a digital designer who's got to reconcile where that analog designer wanted those pins. So if there was an automated way to pass that, we do that through open access, of course, when you look at a mixed signal flow. And so we can handle those constraints very seamlessly from a digital to an analog designer, so that there is no hiccup, there is no miscommunication about what that intent needs to be. So that'd be a couple of examples of intent.
Okay. So now that we've illuminated that, let's talk about these three awards. The first one that we want to talk about is the one that EDI got.
Sure. Now, EDI is an exciting area. Place and route is certain. A lot of people think that you push a button, it's pretty automated, and I think for the most part, At 180 and 130, it's probably mostly true. But 90, where you started to see signal integrity aspects come into play, timing driven, everything became important. Then you started adding timing and signal integrity and power and area and yield and all these different elements coming together. It became quite an issue. And what happened is you started to slow down the process. So EDI system is actually a new entrant for the market, to the market for us. We used to have SOC Encounter, which was very much an older style database and older style of methodology tuned for that 130 nanometer and above, maybe 90 and above. But we started to recognize that for us to be competitive and for our customers to be able to be competitive in their end markets, we had to provide a very fast turnaround time. So things like multi-core became really critical, a backplane of multi-core. Second of all, we had to bring InDesign into the cockpit, we call it InDesign for sign-off, into the cockpit or the vehicle that they're using to implement. So now instead of having a separate sign-off step for timing or for SI, and now we continue to follow that path for physical verification, now for design for manufacturing, and we keep adding this multi-dimensional optimization capability inside of the implementation cockpit itself. It makes getting to the end mark, which is ultimately the tape out with confidence, very straightforward to do. So EDI system really excelled in that pulling together of that end-to-end digital flow. So the market has responded in the sense that we're now engaging in very difficult designs that for companies that would not have thought of Cadence as a player, and I think in many cases probably rightfully so, but now we're getting into these companies and the companies are seeing the value to their ultimate goals, which is profitability and productivity through the design flow. So EDI, we're starting to see a lot of traction with EDI over the last year and a half in particular. An example is that we've seen 270 brand new customers come to Cadence for EDI or Encounter Digital Implementation System, which we didn't have before. And that's a big difference. We're very proud of that.
So you said really difficult SoC designs.
Sure.
Define difficult.
Sure. 40 nanometer is difficult. 40 nanometer with low power is more difficult. 40 nanometer with low power and mixed signal elements, because you have analog blocks on there as well that you have to manage and optimize at a top level, insanely difficult. So that's one flavor of difficulty. Another example of difficulty is when customers try to do something fundamentally new, such as a 3D IC. Now, there's not a lot of those customers out there today. There's a handful of customers that are really driving that leading edge, but that would be considered a difficult design. You have a different methodology for floor planning, a different methodology for analysis, a different methodology for everything you do, and so that would qualify as a difficult design. It's an area, again, where we excel with EDI system.
Okay. So now let's switch over and talk about the award for the parallel simulation.
Sure. So we've been in the analog business for years. It's the hallmark of Cadence. It's really the fundamental core of what we do. Simulation of analog circuitry is also an area of strength for us. Spectre is something that people know of in the industry. It's a household name in our industry, so to speak, for simulation. But it's very detailed and can take some time to run. Accelerated parallel simulation is something that we introduced going back 2 years ago, and now has really started to get some traction. APS, as we call it for short, is, I think the key there is it's integrated into the analog design environment. So anybody who's an analog designer today is using Virtuoso, either the schematic or the layout and the environment. They have the simulation engine built in that's really fast, so multi-core enabled, able to be very accurate, first of all. And if you look at a traditional simulator taking X amount of time, APS would run in a hundredth of the same, a hundredth of that same time. So it's, so it's extremely fast. APS is known to be fast. So every time we get into a benchmark situation, it's a no-brainer. So APS has really caught fire. Moving from a Spectre to APS has been something that's brought a lot of advantage to customers, and clearly it's recognized by the industry. So we're really proud of that product, and we're seeing a lot of growth in that area.
Okay. So now let's talk about the PCB award.
Sure. So PCB is an area that we have a tremendous presence in. I mean, anybody who's doing PCB or packaging for that matter uses a Legro product or an OrCAD product, and those are, again, both household names in the Cadence world and in EDA. So we've been working for 3 years in particular. Our award here is on the PCB signal integrity product line. And for the last 3 years, we've been really driving hard to offer, this gigabit interface for DDRs and also for very high speed, just high speed interfaces overall. And this is where Allegro and the Allegro PCB really came up against the competition and started to really show a distance in terms of what it could do. So Allegro, the cool thing about Allegro is independently as a product, as a point tool, it's very, very strong, right? But the other magic there is that it is connected deeply into our whole SIP offering, which is Silicon in Package, our system in package. And this allows us to tie all of the digital analog design that we do, whether that be pure analog, pure digital, or a mixed signal design, and think about it in context of not just the silicon, but that literally goes in a package, so you got to understand that component, and that package ultimately goes into a board, which becomes a system, which is what people ultimately buy. So the fact that we have these strong technologies for Allegro, particularly in the high end, bodes very well for what we're doing overall with silicon realization, which is to bring intent, abstraction, and convergence to bear through all of our platforms.